Hello and welcome. My name is Jessica Cruz, and this is Lab 4 for Physics 2212. Introduction. Purpose. The purpose is to collect observational data of a magnet falling through a conductive tube of aluminum foil, and to model the magnet or tube's interaction computationally and to compare computational predictions with observed data. Here are some fundamental principles: Frod's law, Lenz's law, and the magnetic flux equation. To the right, we can see Frod's law, and we can see Lenz's law, which is just that negative sign. Here we have a brief explanation of why we have that. The minus sign denotes Lenz's law. EMF is the term for generated or induced voltage. And to the right, we have our magnetic flux equation. And here we have our main results. Our experimental is 1.68 seconds, and our computational is 1.143 seconds. And that gives us a difference of about 0.537 seconds. Okay. Initial conditions. Systems and surroundings. The system is the bar magnet and aluminum foil roll. The surroundings is everything else. Materials for this lab. We needed a bar magnet, a roll of aluminum foil, magnetometer app, and a ruler. We use a ruler to measure our foil, and here are my following measurements. For the length, I got this. Width, I got this. And inner radius, I got this. For the magnet, our mass was this, and our magnetic dipole moment was grabbed from our previous lab. Experiment. Procedure. Mark the north pole of the bar magnet using the app on our phone, the magnetometer. Now with one hand, hold the tube vertically and have the bar magnet just above the top opening. Record the magnet falling through the tube, and now repeat this 4 more times and record our data. Here is my data. Here's trials 1, 2, 3, 4, and 5. And here is our results. And this is our average. Source of error, there could have been possible calculation errors. My measurements might have been off, or my timing might have been off with stopping the stopwatch. Coding. So our coding was pretty big to fit in a slide, so I decided to grab a chunk. And this kind of shows how we calculated flux and the loop that simulated this. And I'm just going to talk through what I did for the coding. So for the coding, I had to initialize conditions, which was the measurements I took. I then had to simulate the tube and the bar magnet. Then I had to calculate the magnetic field of the bar and the magnetic flux. And then I had to simulate the loop by calculating the gravitational force and the magnetic flux. I believe that's shown right here and around right here. After that, I then had to calculate the magnetic force on the magnet and the magnet's velocity and position. And this is what created the graph. If you want to see my coding, here is my website. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? If the conductor was reduced as close to possible to 0, then the induced magnetic field would be much bigger and slow down the bar magnet's fall. What if holes or slots were cut into the tube? How could this affect the recurrence in your model? If holes or slots were cut into the tube, it would decrease the magnetic flux, since the number of turns will be less, which will also lower the magnetic flux.